Welcome back to ECE 501B. Homework number 7 is due a week from tomorrow. Your project is now posted on D2L, and that's due on Sunday evening, the 7th of December, which is basically leading into the last week of class, which includes the last day being the first day of finals. That's why it's set on that Sunday as far as the due date for your project. Today what I want to do is continue with Chapter 7. We'll simply restate the complex vectors inner product space spectral theorem, or the complex spectral theorem, which is 7.9. Then we will review the Cauchy-Schwarz because we'll need that in developing a proof. We will talk about completing the square because we need that in developing a proof. And then we'll get into lemmas 711 and 712. And in particular, the proof of lemma 711 needs to use the Cauchy-Schwarz and completing the proof. Then we'll simply state the real spectral theorem. We'll try to summarize what these spectral theorems mean. Then we'll talk about the structure of this linear operator when we're dealing with two-dimensional real inner product spaces, what that means in terms of a structure of the operator when we look at its matrix representation. We will look at block matrix structure, and then I'm not sure we'll get that far today, but eventually we'll start getting into positive operators. And now when we were talking about inner products, we were using those to talk about length and angle. Now we want to apply some of those same ideas to operators, and we want to think about distance, sort of like length, and direction, sort of like angle. So can we associate with an operator some kind of size, scaling, or distance, and direction? And that will lead us to singular value decomposition. That's sort of where we're headed, and that's something a little bit different from eigenvalues and eigenvectors. But positive operators are now you might think of scaling. How do these operators scale something? And they're operating on a vector, so they're now scaling that vector in some way. Or they act like a scaling. The complex spectral theorem. Suppose V is a complex inner product space and T is a linear operator on that space. V has an orthonormal basis consisting of eigenvectors of that operator if and only if the operator itself is normal. And by normal we mean that the operator commutes with its adjoint, or another way of thinking of an operator being normal is if we compare the norms of that operator on a vector, that's equal to the adjoint of that operator on the same vector. That's now just a restatement of the complex spectral theorem, and we want to think about what we can say relative to the real spectral theorem, or when we're working on the real inner product space. And we'll actually have to specialize this a little bit more than just our operator being normal. And in particular, we'll need it to be something stronger, which is self-adjoint. But here in the complex inner product space, we need T to be normal in order to have a nice set of basis vectors, which are these orthonormal basis. Now, before we get into this, the real spectral theorem, I want to talk quickly or simply restate the Cauchy-Schwarz inequality. We'll talk about completing the square, and those will then be applied in the proof of lemma 711. And so now we have to worry about convenience if we're talking about 711. You didn't catch that convenience store lead in, but All right, so Cauchy-Schwarz. That was back in chapter 6, which says that the magnitude of the inner product is less than or equal to the norm of U times the norm of V, where we were looking at the inner product of U with V, its absolute value. What we are going to use is we're actually going to use the lower limit of that, meaning if we think about the absolute value, we now know that if we bound the inner product, we know that it's bigger than minus the norm of U times V, or it's less than or equal to the norm of U times V. And we're actually going to use the lower bound in our derivation. So when I start, or when we get into one of these proofs, the proof of lemma 711, we will have an inner product, and we're actually going to try to bound that from below, and from below we'll use that left-hand side inequality. Now let's remind ourselves about this concept of completing the square. And really what we're looking at is trying to make sense of a particular expression. So suppose we have the following expression, which is, let's say, x squared minus alpha xy plus y, whoops, let me include another coefficient, beta times y squared. We want to basically complete the square so that we can now write this as a sum of two squares. That's the idea. And to do that, let's just remember that we can look at taking those first two terms and trying to use those to create a new expression, which we will then be having to square, and that's going to then impose or mean that we have to add something else to that equation. We're basically going to add 0 to that equation. But the observation that we want to make is if we look at x minus alpha over 2 times y and square that, then we simply get x squared minus 2 times alpha over 2 x times y plus alpha over 2 squared y squared. Or the part that we want is to go ahead and multiply the 2 through, and we now have x squared minus alpha xy plus alpha over 2 squared y squared. Meaning we are interested in this piece of that term or that expression, because that's what appears in our original expression. We now need to simply use this note to complete the square in this beginning expression. So now look at what we started with before, which was x squared minus alpha xy plus beta y squared. Now we know we can make that, or that's equal if we add 0 to it, and the 0 that we are going to add is going to be associated with that piece. We're going to add a positive amount of that and a negative amount of that, and that's then adding 0. So we now have x squared minus alpha xy plus alpha over 2 squared y squared minus alpha over 2 squared y squared plus beta y squared. That's just equal to 0. So we've added 0 to that expression, but what we can remember is that this piece is what we just had up above for the quantity x minus alpha over 2 times y squared. Or we can now rewrite that expression as x minus alpha over 2 squared plus beta minus alpha over 2 squared y squared. In our derivation or in our proof, this is always non-negative. But we will want to look at when this guy is non-negative. And that will be true as long as beta minus alpha over 2 squared is bigger than or equal to 0. Or let's just say it's a strict inequality and just say that we want beta minus alpha over 2 squared to be bigger than 0. Or if we multiply that out, we see that we have beta minus alpha squared over 4, or beta is greater than alpha squared over 4, or 4 beta is bigger than alpha squared. And I might write that actually as alpha squared is less than 4 beta. If we have alpha squared is less than 4 beta, then we can say that that original expression right here is non-negative, because we've now split it up into two pieces that each piece is non-negative. All right, that will be one of the pieces of this proof of the following lemma. Again, we're getting two lemmas so that we could then basically conclude or talk about the real spectral theorem. Lemma 711. Suppose we have a linear operator T, and let's assume that that operator is self-adjoint. Suppose that alpha and beta are real numbers, and they are such that alpha squared is less than 4 beta. And that should look familiar with what we just wrote down. We are writing some equation that includes those coefficients alpha and beta. Then we have T, which is self-adjoint, and we have alpha and beta such that alpha squared is less than 4 beta. Then the following operator, T squared plus alpha T plus beta I, is invertible. That's lemma 711. Let's look at the proof of that. So now we can assume that alpha and beta are real, with alpha squared less than 4 beta. And let's pick a non-zero vector, v, and v is a non-zero vector in our vector space V. Let's now look at the following inner product. Suppose we have T squared plus alpha T plus beta I times V inner product with V. And we want to say something about that inner product. Well, we have 3 terms in the first slot. Why don't we break those out or use linearity of the first slot? to say that that expression is now t squared v, inner product with v, plus, and we have homogeneity the first slot, which will pull out that scalar alpha, tv with v, plus, again using the homogeneity of the first slot, beta times the inner product of v with v. Let's now use a part of that t squared and move half of it over to the second slot. So we're going to write t squared as t times t. And if we have t operating on tv, let's just move that t to the second slot. And what's that produce in the second slot? Here we're going to simply apply the definition of our adjoint. So that now we're left with tv in the first slot, and t we're moving over into the second slot. That now gives us t adjoint v plus alpha tv with v plus beta v with v. We made another assumption on t. We said it was self-adjoint. Let's now use that relationship, meaning whenever we see the adjoint, let's just replace it with t, since if it's self-adjoint, t is equal to t dagger. So we now have tv plus alpha tv plus beta v. We have a couple of inner products that have the same entry in both slots. Let's just apply the norm definition to those. We now have the norm of tv squared plus alpha inner product, or times the inner product of tv with v, plus beta times v norm squared. Now we want to bound this from below using Cauchy-Schwarz, which means now we have this inner product of tv with v. Applying the lower bound, from Cauchy-Schwarz, then that's greater than or equal to tv squared minus alpha tv v plus beta v squared. Now we want to complete the square, because we have, let's say, x minus alpha xy plus beta y squared, or we have x squared minus alpha, just like we had in our earlier discussion of completing the square. If we now complete the square, well, let me go ahead and keep the inequality so that we just have that bounding the leftmost entry. We now have x squared, which we are writing here as the norm of tv, minus the absolute value of alpha over 2 times the norm of v squared. Then we need to add, or actually subtract, alpha squared over 4 norm of v squared. That's the part of adding 0 in our completing the square, and now we just drop down the plus beta v squared. We keep this first term, and we now add into that beta minus, whoops, and what we are saying from before is if we impose that relationship on beta and alpha, we can make that scaling factor on the norm of v squared be positive if beta minus alpha over 4 is positive, or 4 beta is less than alpha squared. If that's the relationship between beta and alpha, we can now conclude that that leftmost entry is greater than 0. So now we know this operator times v, inner product with v, is greater than 0 from that development or discussion. We can now, let's just remind ourselves of what we had. We had t squared plus alpha t plus beta I times v with v is now greater than 0. What can we say about the vector v as a result of this relationship and how v is related to that operator? If we have an operator times a vector, and that now gets inner product with the same vector, and we know that it's bigger than 0 when v is non-zero, what's that saying about that operator? Pardon? It's injective, isn't it? Or that there's no null space, or there's only a trivial null space. There's no non-trivial null space. So therefore, v cannot be in the null space of that operator, where the operator is t squared plus alpha t plus beta I. If v did belong in the null space, then that would be the 0 vector, and anything with the 0 vector inside the inner product becomes 0. And we've now said that with beta and alpha enjoying the relationship that we imposed on them, we now know that v can't live in the null space of that operator. Or what was stated in class just now is that t squared plus alpha t plus beta I, if it does not possess, if it only possesses a trivial null space, then that operator is injective. And if we have an injective operator, there's some relationship between injective, surjective, and invertibility, isn't there? They're all equivalent, right? So now we can say that t squared plus alpha t plus beta I is in fact invertible. And that's what we were trying to show in that lemma, or with that lemma. If t is then self-adjoint and alpha and beta are related in that manner, then we can state that that operator with a linear combination of t and the identity operator is invertible. Lemma 712. Again, assume t is a linear operator that's self-adjoint. Then t has an eigenvalue. And now that's generic in terms of whether we were on a complex inner product space or a real inner product space. I will refer you to the book for that proof. But now, as long as t is a linear operator and it's self-adjoint, then we are assured that it has an eigenvalue. And now we can start talking about the real spectral theorem, where spectral is really referring to the spectrum, which is another way of talking about eigenvalues. The real spectral theorem is the following. Suppose V is a real inner product space and T is an operator, linear operator on that real inner product space. Then V has an orthonormal basis of eigenvectors of that operator T if and only if T is self-adjoint. Because from the last lemma, we know that it has eigenvalues if it was self-adjoint, and now once it has eigenvalues, we can associate these eigenvectors, which are orthonormal or can be normalized because we're working on an inner product space. So let's now move into really trying to understand more of that without going through the proof. Let's just try to see what it is that we now have available to us in terms of these complex spectral theorem and the real spectral theorem. And really what that allows us to talk about are sort of nice basis vectors or diagonal matrices. One is that normal matrices have diagonal representations or maybe I should say normal operators have diagonal matrix representations. Maybe that's what I should say. Normal operators have diagonal matrix representations on complex inner product spaces. So if we're dealing on a complex inner product space and we have a normal operator, then that operator has a matrix representation that's diagonal, which is a nice way of expressing or manipulating matrices. If we have self-adjoint matrices, well, or self-adjoint operators. Let me clean this one up too. Self-adjoint operators have diagonal matrix representations on real inner product spaces. So if we have an even more specific operator in that it's self-adjoint, then it can be diagonalized on a real inner product space. So here is our sort of summary of what we now have available to us. V, this inner product space, has orthonormal basis of eigenvectors of linear operators T if and only if A, V is a complex inner product space and the operator T is normal, or B, V is a real inner product space and T is self-adjoint. So if we're dealing with real inner product spaces and we want to have a diagonal matrix representation, then we need our linear operator to be self-adjoint. That's fairly constrained. We don't have to be quite that constrained on a complex inner product space. We only need the operator to be normal, which means that it commutes with its adjoint. Doesn't mean it's equal to its adjoint. It just means that it commutes, the operator commutes with its adjoint, so that's not quite as restrictive as having the operator being self-adjoint. What can we say, or can anything be said, for a more general case when we have real inner product spaces? What about more general case of V being a real inner product space and T being normal, not self-adjoint? So now, is there anything that can be said about this operator or its matrix representation if we're on a real inner product space and T is normal but not self-adjoint? Can we say anything? Thumbs up or thumbs down? 50-50 chance. Luckily, the answer is yes. So now let's look at the lemma that tells us what can be achieved when we do have a normal operator on a real inner product space, and that is given to us in lemma 15 of chapter 7. Here we're given V, and let's just work on a two-dimensional real inner product space, because then we'll start talking about block diagonal matrix representations, and so once we know that it works for 2D, then we're pretty well good to go. So given V, a 2D real inner product space, and a linear operator T on that two-dimensional real inner product space, the following statements are equivalent. I. T is normal, but not self-adjoint. The matrix representation of T with respect to any orthonormal basis is of the following form, where we have A minus B, B, A, with B not equal to 0. And 3, there is some orthonormal basis with B positive. Really what this is saying is if we know that we can create linear operators on real inner product spaces that do not have eigenvalues, these rotations. But those can be written in terms of a real matrix where A is really the real part of the eigenvalue and B is the imaginary part. This is now a two-dimensional real vector description of complex eigenvalues associated with a matrix that a real matrix or an operator that's working on a real inner product space that does not have any eigenvalues. Meaning that particular matrix structure is very special. A minus B, B, A, that's now representing some complex eigenvalues if you allowed the field of numbers to be complex, which we're not allowing to have happen if we're working with real inner product spaces. What we will want to be doing now is using that information to basically not here with these spectral theorems, we were guaranteed of having a diagonal matrix representation with a complex inner product space, T being normal, and with a real inner product space, T being self-adjoint. Now we're saying if we do not have T being self-adjoint, but it's normal on a real inner product space, we can't diagonalize, but maybe we can block diagonalize. And the block diagonal structure that we want is going to be these two-dimensional little blocks on the diagonal. That being said, we need to introduce some block matrix notation. By that, I mean we could define a matrix D that let's say is 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. And I'm just using the same values for my elements just because I'm boring. But here, let's say this is now 2, 2, 2, and 2, 2, 2. And maybe this is 3, 3, 3, or 3's in those 9 elements of the lower block. We are going to refer to that as a matrix that's A, B, C, and 0. That's a block matrix notation, where the A block, I hope it's clear, is the 2 by 2 submatrix of 1's. The B is the submatrix that's 2 by 3 of 2's, and the C is this square matrix 3 by 3. And as I said, all of these elements don't have to be equal to enjoy this block structure, block matrix structure. All elements of these submatrices are not necessarily equal. So now what we want to do is try to see what we can achieve or accomplish if we allow our thinking to be not always just a diagonal matrix, purely diagonal, but a block diagonal. That will allow us, we'll now be able to start representing operators by block diagonal matrices, not just restricting ourselves to diagonal matrices. So in chapter 6, if we go back that far, let's just say in chapter 6, we saw the following. If T is a linear operator on V, and U is invariant under T, so U is now a subspace in, let's say, capital V, in the vector space V, and we have a linear operator T on that vector space V, but now we're saying that U is invariant under T. If we operated on anything in U with this linear operator T, where are we going to end up? In the same subspace U. So now if we pick any vector in U, if we operate on that vector with T, it's going to end up back in U. It may not be equal to the same vector, but at least it will be made up of linear combination of the vectors spanning the subspace U. So if T is a linear operator on V and U is invariant under T, then the orthogonal complement to U, the subspace U, is invariant under the adjoint of our linear operator, T. What we can now do is we can actually show or prove a little bit stronger relationship if our operators are normal. Because in chapter 6, we were just worrying about subspaces and we weren't saying anything about the characteristics of our operator t. Now, if we restrict those to being normal operators, what more can we gain from that? So let's look now at lemma 7, or proposition 18 in chapter 7. This says, suppose that we have a linear operator t and it's normal. And suppose U is a subspace of V that is invariant under T. Then we have several equivalent or several statements that can be made. One is that the orthogonal complement of the subspace U is also invariant under T. The original subspace U is invariant under the adjoint of T. So now we're starting to show sort of a little bit more than what we had before. C is if we look at the operator T restricted to the subspace U, and we form the adjoint of that operator, that's the same as looking at the adjoint of our original operator restricted to the subspace U. We can also look at the operator T restricted to U, and it is in fact normal on U, and T restricted to U perp, or the orthogonal complement to U, is also normal on U perp. So let's look at some of these statements in the form of a proof. Suppose we now have this list of vectors, E1, E2, E sub m, and they're more than just a list of vectors. Let's let those be an orthonormal basis of our subspace U in this proposition. And that means our subspace is M, or Michigan, in size. E sub 1, E sub 2, E sub m, let that list be an orthonormal basis of U, and we're assuming that U is a subspace of V. So now if we wanted a full set of basis vectors on V, we would need to extend this original list M out to, let's say, N, if N is the size of our underlying vector space, capital V. So let's now extend this list, E1, E2, E sub m, with, well, actually I'm going to make it even longer. So I'm going to make this little n in length. So now the total is M plus N, Michigan plus Nevada. So that this list, E1 through EM, F1 through FM, for an orthonormal basis on the underlying vector space V. since U is invariant under T, what do we know about T E sub j? And E sub j is some vector in that first list of vectors E1 through E sub n. If if U is invariant under T, and E sub j is in U, what do we know about the result of mapping E sub j through T? Or how could we express that result? Do we have a linear combination of vectors that linear combination has to be equal to T E sub j? And what list of vectors are going to be combinable or expressible to create T E sub j? E sub 1 through E sub m. So now is expressible in only E1, E2, E sub m. That then says that if we looked at the matrix representation of T, then if this is now E1, E2, E sub m, in terms of the lengths, and now we've extended it to F1, F2, F sub n, then we know that we have at least this kind of block matrix structure. Since anything that's spanned in E1 through EM has to remain in that collection or linear combination of those vectors, we know that the matrix structure of our linear operator has to have this block upper structure form, or a block A and all zeros below. This then allows us to make the following observation about certain norms. So note that since any T E sub j we can write as A1j E1 plus A2j E sub 2 plus A sub mj E sub m. We know that's true. So now we have this T E sub j as some linear combination of E1 through EM. Can we make any, let's say, more concise notation-wise, any more a different way of writing the norm squared of T E sub j? Or we now have this falling inside there. We now have a linear combination of orthonormal vectors. These orthonormal vectors, what are the lengths of those? They're 1. So that now if we have those sitting inside this norm squared, each of those, if we now looked at that relative to the inner product, all of these cross terms are going to go away. We will simply have this equaling A sub 1j squared plus A sub 2j squared plus dot 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 plus A sub mj quantity squared. We just have the absolute value of these complex scalars squared. That will be the norm of t e sub j squared. Or we could write that in a summation form as the sum from I equal 1 to m of a sub ij quantity squared. Now, suppose we looked at all of those possible t sub ej's, or the sum of those. Suppose now we looked at j equal 1 to m of t e sub j squared. Now we have a double summation on the right-hand side. We have a summation from j equal 1 to m, and a summation from I equal 1 to m of a sub ij quantity squared. Or this particular summation ends up being a sum of elements squared in the original sub-block A, or in block A of that matrix representation of our linear operator T. So now if we wanted to find the norm of this operator squared, or the sum of that over all of these orthonormal bases, we could simply sum up all of these elements in A in that matrix squared, their absolute value squared. So that's what we have for that particular expression. Now, we can relate that to what we have when we're dealing with an adjoint operator. From our study of adjoints, we saw that rows of the matrix representation of T will be expansions of T dagger E sub j, meaning rows and columns get interchanged when we talk about adjoints. So that now if somebody gives us T dagger E sub j, this is now a sub 1j E1 plus a sub 2j E2 plus a sub mj E sub m plus b sub 1j f sub 1 plus b sub 2j f sub 2 plus b sub nj f sub n. Meaning now if this is the matrix representation of T, the matrix representation of T dagger is the transpose. And so now if we needed to apply that matrix representation to any of these vectors E sub j, it's now going to be represented by E1 through EM plus F sub 1 F sub n linear combination. Now what happens when we take T dagger E sub j squared? We get the same sum of all of these coefficients absolute valued squared, but now we have more coefficients. We now have absolute value of 1j squared, absolute value of 2j squared, etc., plus all of the b's. So now we have this sum. If we looked at all of those possible E sub j's, all m of those from j equal 1 to m, now we have this sum of elements squared in both blocks A and B. If we looked at all of the sums over j from 1 to m. But we started in this proposition, we started with t being normal. And one of the relationships that we know is true if an operator is normal is we know that the t E sub j is equal, or the norm of that is equal to t dagger E sub j for all j. That means then that if we look at the sum of j equal 1 to m of t E sub j squared, that better be equal to the sum of t dagger E sub j squared. If that's the case, then what can we say about this right-hand side when we look at it compared to this right-hand side? This one, when we summed t E sub j squared, we just had all of these absolute value of the elements in block A squared summed up. Now, when we simply look at the adjoint of t E sub j, we get the sum of all the elements in block A and B absolute value squared. But now we're saying that those two sides have to be the same. The only way that they can be the same is for what to be true. What do we know about the elements squared in block B? If this piece, that right-hand side, because we know the left-hand side there has to equal the left-hand side here, so the right-hand sides have to equal, and here they're the sum of all of the block A, here they're the sum of block A and block B. That means that the sum of the elements squared in block B are in fact 0. Well, if that's true, then we know that all the elements in block B are 0. And now we actually have a more structured matrix representation of the linear operator T. Now we know that we have A, 0, and this block is 0, and here is a C. So that we now have E1 to EM, F1 to Fn. This is E1 to EM, F1 to Fn. We now know that what we've shown, or this implies, T F sub k is now actually going to be in the span of those F's. For all k. But we actually know that that list of basis vectors that we use to extend the original subspace orthonormal vectors E1 through EM to make it all of V, this is actually a basis of the orthogonal complement to our original subspace U. And now we know that T operating on any vector in U perp remains in U perp, so that now U perp is invariant under T. And if you've forgotten, I'll remind you that was statement A. A is now proved. A was the following. If we started with this linear operator T and it's normal, and U is a subspace of V that's invariant under T, then U perp is invariant under T. And we showed that by this argument of the block matrix structure of the matrix representation of that linear operator T. B, is U invariant under T dagger? Let's see if we can show that. So now, if we look at B, the matrix representation of T dagger is the conjugate transpose of the matrix representation of T. So we now have that the matrix representation of T dagger is also block diagonal, where this is now E1, E2, E sub M, E1, E sub M, F1, F sub N, and this is F1, F sub N. But what does this show? Now we can show the same kind of argument that if we start with some vector E sub j and this associated with the upper left corner of this matrix representation of T dagger, where does that fall in terms of spans? If we now start with a vector that only has, let's say, non-zero entries in the top piece, the first M piece, and we hit it with this matrix, we're going to stay in that top M piece, aren't we? So now we are simply going to be in the span when we operate, and this is the matrix representation of T dagger. We are going to stay in the span of those original basis vectors, E1 through E sub M, and that's true for all J. And that now says that U, which these E1 through EM were basis vectors for U, now if we have anything that starts there, it stays there when we hit it with, or if we operate on it with T dagger. So U is now invariant under T dagger. Which now allows us to say that B is proved. Let's now move on from that proposition and just look at some particular concepts dealing with block diagonal matrices. Since these we will use in the future. Block diagonal matrices are square matrices, or are square, what I should say, square blockwise matrices of the following form. A, B, C, I'm getting very creative, down to, let's say, K, and everything else is 0. With A, B, all the way to K, square submatrices on the diagonal. Some statements we can make about block diagonal matrices. A diagonal matrix is in fact a special case of a block diagonal matrix. So a diagonal matrix is a special case of what we just said was a block diagonal matrix. What are the dimensions on those blocks A, B, C through K if we have a diagonal matrix? If this matrix is diagonal, more than just block diagonal, how big is capital A in terms of dimensions? Now capital A can't have anything in the off diagonal. And if it's a matrix and it has nothing on the off diagonal, it's now a 1-by-1 matrix. So all of these submatrices for a diagonal matrix, all blocks are 1-by-1. That's a special case of a block diagonal matrix. We can also say that any matrix, no matter what it looks like, is expressible as a block diagonal matrix. It's just now we would have simply one big block. So it's important to know the size of these subblocks along the diagonal. Need to know the size of these subblocks. What do we know about the product of two block diagonal matrices? Suppose A is A1, A2, A sub M. B is B1, B2, B sub M. With these A sub J's the same size as the B sub J's for all J. That's the only time that it really makes sense. If that's the case, then AB, this matrix product, remains block diagonal. And it has the form of AB is now A1, B1, A2, B2, A sub M, B sub M, with everything else being 0. And the book will show different things about that. I may write that down and present that to begin with on Monday.